This lesson is about complex numbers. What are square roots? How do we get them? Well, square roots are numbers that look like this, where the symbol on the outside of the number is called the radical symbol, and the number underneath the radical symbol is called the radicand. When we are trying to find the square root, we're asking ourselves, what number can we multiply times itself to get that number? So in this example, the square root of 4 would be 2 because 2 times 2 equals 4. But the square root of 4 could also be negative 2 because negative 2 times negative 2 is also 4. That's why when we're taking the square root of a number, like for example, if I wanted to find the square root of 9, I would say that the square root of 9 is plus or minus the square root of 9, which would be plus or minus 3, because 3 times 3 is 9, but negative 3 times negative 3 is also 9. Now, in past math classes, when we got to a negative under a radical, we would just stop and say there's no real root. But today we're going to define what it means to have a negative under the radical. The imaginary unit I is defined as I is equal to the square root of negative 1. And then if we were to square both sides of that, if I were to square the I and square the square root of negative 1, we know that square and square root cancel each other out, so I squared is equal to negative 1. So because of this definition, we are now able to deal with negatives under the radical. Using the imaginary unit I, we can express the square root of any negative number as a real multiple of I. For example, if I have the square root of negative 25, I can split that up into the square root of negative 1 times the square root of 25. Then, using the definition, we can change the square root of negative 1 to I, and then we know that the square root of 25 is 5, and then we would just put the I after it to get our answer, which is 5I. Now, we write our answer just like we would any polynomial when we have a variable, a monomial with a variable. You know, we would, if it were an x, we would write it as 5x, not x5. So it's the same thing whenever we have the imaginary unit I, we write it as 5I, not I5. There's a few other definitions that we need to talk about. Complex numbers are the set of all numbers in the form a plus bi, where a and b are real numbers and I is the imaginary unit. In this complex number, a plus bi, a is the real number part, and b is the imaginary number part. In the imaginary number, the complex number a plus bi is called an imaginary number as long as b does not equal 0. Because if b equaled 0, then that would make that part of the complex number go away, and you would only have a real number part. So it would no longer be an imaginary number. That's why it says that b can't equal 0. It has to be some number other than 0. Now, a pure imaginary number is an imaginary number in the form bi, which means that there is no a part, there's no just real number part. So that answer that we just got, that 5i, that was a pure imaginary number because there was no real number connected to it. Some notes with this are that a complex number is said to be simplified if it's in the standard form a plus bi. So when you're writing your answers for your complex numbers, you should always put the real number first and the imaginary number last. If b is a radical, we write I before the b because when we look at these two examples, it's hard to tell where the I is located. It's hard to tell if the I is under the radical or not under the radical. In this first square root of 5i, the I is not under the radical. In this one, it is under the radical. So because it is so hard to tell where it's located, when it contains a radical, we write it like this. We put the I in front. So if there's not a radical, we put it behind the number, just like 5x or anything like that. But if it's a radical, we put it in front of the radical just to alleviate confusion. Two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. This is just kind of common sense. This just means if we have two complex numbers like a plus bi and c plus di, they're only equal if a and c are equal and b and d are equal. Now let's do some operations with complex numbers. When we're adding or subtracting complex numbers, we do the operations the same way that we would if we were dealing with polynomials, meaning that we combine like terms in order to simplify. And if we have parentheses, we can drop the parentheses if there's nothing in front of the parentheses, or if there's just a plus sign in front of the parentheses. But if we have a negative sign in front of the parentheses, that negative needs to be distributed to everything after the parentheses before we combine like terms. So let's do that in a few examples. Okay, so in this first example, we're going to add these complex numbers. Because the 5 minus 2i has nothing in front of it, we can just drop the parentheses. And because the 3 plus 3i has a plus in front of it, when I distribute the plus sign, it doesn't change anything. So basically, we're just dropping the parentheses in that one also. Now we want to combine our like terms. So our real numbers are 5 and 3. 5 plus 3 is 8. And the imaginary numbers, negative 2i and positive 3i, when I combine that, I get a positive 1i. But just like when we're dealing with variables, the 1 is understood. And remember that we need to write our answer in standard form, meaning that the real number part needs to go first and the imaginary part last. So this would be our answer in standard form. In the next example, we're subtracting two complex numbers. So the first set of parentheses we can just drop because there's nothing in front of it. But the second set of parentheses, we're going to distribute the negative. And that gives me a negative 12 plus I. When I combine my like terms, my real numbers, 2 and negative 12, would give me a negative 10. And then positive 6i and positive I would give me a plus 7i. Again, make sure that your real number is first and your imaginary number is last. And that's my answer in standard form. Multiplication of complex numbers is performed the same way as multiplication of polynomials. We do this by either distributing or using the FOIL method. Alright, let's find the products. In this first example, we have 7i, and it's being multiplied times the binomial 2 minus 9i. So I'm going to distribute 7i to both of those terms in the parentheses. And we multiply just like we would if those were any other variables besides I. Alright, so 7i times 2 would give me 14i. Then when I multiply 7i times negative 9i, I get a negative 63, and I times I would be I squared. Okay, here's where things get a little different than they would with a polynomial. Remember, we defined I squared to be negative 1. So this is the same thing as negative 1. Now, this negative 63 and the I squared are being multiplied. So now that I changed the I squared to a negative 1, I'm going to multiply that negative 63 and negative 1, so that gives me a positive 63. Okay, we're almost done. Just remember to write our answer in standard form. The real number needs to go first. So my answer is going to have the 63 first and the 14i last. And this is my answer. All right, let's look at B. Since these are two binomials, I'm going to FOIL. Multiply the first two, that gives me 30. The outer two would be a negative 35i. The inner two, that would be a positive 24i. And then the outer two, the last two would give me a negative 28i squared. Okay, so first I'm going to combine like terms. These two terms in the middle are like terms because they both have i's. So I'm just going to bring down the 30. And then negative 35i and positive 24i would be a negative 11i. And then I'll bring down the negative 28i squared. Well, just like in the previous example, we're going to change that I squared to a negative 1. All right, so then I'm going to multiply the negative 28 and the negative 1, and that gives me a positive 28. Now I need to combine those two real numbers, and they need to go first in order for my answer to be in standard form. So that would be 58 minus 11i for my answer. Complex conjugates are used whenever we are trying to get rid of a complex number or to make it a real number. So a complex conjugate is when we have a complex number like this, a plus bi, and the complex conjugate would be exactly the same except for we change the sign in the middle. Now, the reason why we do that is if we look at these examples here, if I multiply two complex conjugates times each other, I multiply the first two terms and that gives me a squared. Well, when I multiply the outer and the inner terms, that gives me a negative abi and a positive abi, which cancels out the middle terms. And then when I multiply the last two terms, that would give me a negative bi squared. Well, that I squared is a negative 1, so that would just give me a plus b squared, which means all of the i's go away. Of course, it would be the same thing if I multiplied a minus bi times a plus bi. It just gets rid of all of the imaginary numbers. Now, we would want to do that when we're dealing with fractions, because if you'll remember, we can't have a radical in the denominator of a fraction. And remember, we defined I to be the square root of negative 1, which is a radical. So if we have an I in the denominator of a fraction, we can't leave it like that because that's a radical, and we can't have radicals in the denominators of fractions. So we cannot leave I in the denominator of a fraction. So here we have an example, 5 plus 4i divided by 4 minus I. Well, this is a radical. We have to get rid of it. And the way that we get rid of it is by multiplying by its complex conjugate. So, like I said, the complex conjugate looks exactly the same except for the sign in the middle is different. So since this is 4 minus I, the complex conjugate would be 4 plus I. Now, remember, when we're dealing with fractions, whatever we do to one part of the fraction, we have to do the same thing to the other part of the fraction. So since we're multiplying the denominator times 4 plus I, we have to also multiply the numerator times 4 plus I. Okay, so let's do this. I'm going to start with the numerator. So these are two binomials, so I'm going to FOIL, and that gives me 20 plus 5i plus 16i plus 4i squared. Now, you could go down to the bottom and start working on the bottom, but I like to go ahead and finish when I'm dealing with a rational expression or a fraction. I like to go ahead and complete one part before I go to the other part. But it doesn't matter, however you would like to do it. So I'm going to finish this numerator first. So I want to combine these like terms, and then I'm also going to change this I squared to a negative 1. Alright, so that gives me 20. When I combine my like terms, that gives me a plus 21i. And then positive 4 times negative 1, that would be a negative 4. Okay, so again, I'm going to combine like terms, the 20 and the negative 4, that would be 16 plus 21i. Okay, and that's as far as I can go with the numerator for now. So let's move down to the denominator. These complex conjugates, I'm going to multiply these times each other. 4 times 4, that's 16. And the outer 2, that would be a positive 4i. The inner 2 would give me negative 4i. And the last 2, that would be a negative I squared. Well, just like I said, in any complex conjugates, the 2 middle terms are going to cancel out. That cancels, and then also this I squared turns to a negative 1. Okay, so I'm left with 16, and then that negative 1 times that negative I squared, so that's like a negative 1, gives me a plus 1. When I combine those, I get 17. Alright, to write this in standard form, I need to separate these two terms. And so that would be 16 over 17 plus 21 over 17i. Now, if either of these fractions could be reduced, you would want to reduce them. These can't be reduced, so this is my answer in standard form. Alright, the principal square root is defined by the square root of negative b is equal to I times the square root of b. For instance, the square root of both 4i and negative 4i is negative 16. The principal square root of negative 16, I just read that incorrectly. The square of both 4i and negative 4i is negative 16. If I were to multiply 4i times itself, I would get negative 16. If I were to multiply negative 4i times itself, I would get negative 16. But the principal square root of negative 16 is 4i, not negative 4i. So when we are using the principal square root, that just means we're going to use the positive root. When we're performing operations with square roots of negative numbers, the first step is to express all square roots in terms of I, and then perform the indicated operations. So I'm going to show you what happens when we do it correctly and when we do it incorrectly. If I were to multiply the square root of negative 25 times the square root of negative 4, the correct way to do this is to take the negative out as an I, so that would be I times the square root of 25 times I times the square root of 4. Alright, so that's our first step. Then we can go ahead and finish solving this. Square root of 25 is 5, so that would be 5i. The square root of 4 is 2, so that's 2i. When I multiply those together, I get 10i squared. And we know that I squared is negative 1. So when I change the I squared to a negative 1 and multiply it times 10, that gives me a negative 10. That is the correct answer. Now let me show you what happens if I do it incorrectly. If I don't take the i's out first and I multiply negative 25, the square root of 25, times the square root of negative 4, when I multiply the two radicands together, I would get the square root of 100 because negative times negative is positive. And we know that the square root of 100 is 10. Well, that is incorrect. The correct answer is negative 10. But we got the incorrect answer because we didn't take the negatives out first. So it's important that you do that as your first step when dealing with negatives under the radical. Alright, perform the indicated operations and write the results in standard form. So our first step is to take the negatives out as I. And these are not perfect squares. So we still need to reduce these radicals. The biggest perfect square in 27 is 9. 9 times 3 is 27. And the biggest perfect square in 48 is 16. 16 times 3 is 48. Okay, so I'm going to take out those perfect squares. The square root of 9 is 3. And the 3 stays under. The square root of 16 is 4. And the 3 stays under. Okay, remember when we are adding or subtracting radicals, as long as the stuff on the end looks the same, I squared root of 3 and I squared root of 3, we can add the coefficients or the numbers in front. So the stuff on the end stays the same, we just add the numbers in front. 3 plus 4 is 7, so that's 7I square root of 3, and that's my answer. Alright, here we have a complex number, a binomial, squared. Alright, remember when we square a binomial, we don't distribute the square. We write it twice and FOIL it. Okay, so if I FOIL this, that gives me a positive 4. Then that's a negative 2 square root. Oh, I'm not doing the right thing. Okay, so what's our first step? What did I say our first step was? To take the negatives out. Okay, so let's do that first. Otherwise, we're going to get a wrong answer. Okay, so I'm going to take these negatives out as i's. And then FOIL. Okay, so now that gives me a 4. And this would be negative 2I square root 3. Again, we have a negative 2I square root 3. And the last two, when I multiply those, that gives me an I squared and the square root of 9. Okay, let's simplify this. I'm going to combine these like terms, change this to a negative 1, and we know that this equals 3. Okay, so I have 4. When I combine those like terms, that gives me a negative 4I square root of 3. And then that negative 1 times 3, that's negative 3. When I combine my like terms, 4 minus 3 is 1, and that's minus 4I square root 3. And that's my answer. Alright, we have one more example. This is division. So the first thing I'm going to do here is separate each numerator into a separate term by putting the denominator underneath each part of the numerator. So that's negative 14 over 2 plus the square root of negative 12. Again, I'm going to take that negative out as an I, and the square root of 12 over 2. Okay, so now we can deal with each part separately. Negative 14 divided by 2 is negative 7, plus this 12, we know that 12 is the same thing as the square root of 4 times 3. So the 4 comes out as a 2, so that would be 2I square root 3 over 2. Now, in this fraction, as long as there's no pluses or minuses in between the numbers, we can simplify the fraction. So those 2's will cancel out, and my answer in standard form is negative 7I square root 3.